So all presentations are here, and when it will be turned.
I sent it to you already.
Okay, then let me bring it up so that we do not waste time on. And let me briefly explain what Levi will be presenting. We can use it next year, or you can introduce this which competition you are participating, right? So there is a local conference presenting on which about this time one can get a check to present the same stuff on the American Chemical Society National Meeting. And this year is a little too late, but next year we can, well, maybe Daniel knows how to submit post deadline, but
it's tomorrow at 8:30, so that would be pretty.
Does another deadline have to meet?
No.
Oh, okay.
No.
Okay. Yeah. Don't scare me with that. I hate deadlines.
So should the microphone?
The microphones are somewhere on the top.
But it looks like
No.
Now mute.
The way to check microphone is to
okay.
And see if it goes up.
Okay, so basically I'm trying to study the grafting of diazonium on the surface of silicon. So of the record in our group, basically I was trying to study the grafting of diazonium on the carbon nanotube surface. But since the carbon nanotube is very stable, it is not reactive, so my computation work does not work. So that's the reason we switched to the silicon surface. This is a mechanism, very old paper. Basically, this is the surface, and the surface silicon is passivated by hydrogen, and this is the diazonium molecule. So this is a cation, and this is anion. Under some certain conditions, there will be charge transfer from the surface to the molecule, and because of this charge transfer, the surface is now positively charged. And this diazonium cation is not radical. So since it is radical, it is very reactive. So we see the breaking of nitrogen and carbon bond. In this way, we have a complete nitrogen 2 molecule. And we also have a phenol radical. And on the surface, this hydrogen can become a proton. So the proton can react with the anion to form a, like here, to form a HBF4 molecule. So right here we have two kinds of radicals. On the surface we have a silicon radical, and here we have phenol radical. And this radical can just combine with each other. In this way, we have the functionalization by the diazonium.
So what makes the silicon on the surface a positive radical in this? Oh,
because there is
electron goes up. Never mind.
Yeah, there is a charge transfer.
I just had a question about like the brackets in the middle one. Usually, I thought the brackets or like whenever you mention organic chemistry, always meant resonance structures. But I guess for this one, it doesn't mean resonance structures, right?
I guess this is just some intermediate step.
Oh, it's just, oh, okay. Sorry. Thank you for clearing that up.
So here is my model. So the surface I choose is also silicon 111, and this is diazonium cation, and this is bromide. So I cannot remember the distance, but I guess probably it is like 4.5 angstrom for the molecules of this. And I first run just geometry optimization, and then I run room temperature ab initio molecular dynamics. The reason I run room temperature ab initio molecular dynamics is just to sample initial geometries from trajectory. So like this is the one trajectory I select from the room temperature and empty trajectory. So this is at 800 femtosecond. In the next step, I use this geometry as input for high temperature AIMD calculations. And also in the AIMD calculations, I keep all these atoms fixed, but also allow the very top atoms to relax. So this is
So what are the challenges? Why simulation is needed? What is not clear with this reaction?
I guess they have some experimental evidence for the proposed mechanism, but I guess there is no computational study on it.
Even if we do not see challenge right now, we need to make up one. Just formulate what is not clear or what. Right now, no one of us know what are the results, but you can right now declare main result and tell that absence of knowledge about is a challenge. So like, would it happen at low temperatures? Would it be like sufficient activation, or how much this function group will affect electronic properties? It's like we do it because we are curious and because we want to justify methods, but for readers it is so much easier to follow the pattern of like, here is the goal and we use different tools to achieve it.
So what is AIMD?
Just every initial molecular dynamics.
Oh, okay.
So this is some profile from high temperature and calculations. So for the high temperature, here we use 2000 Kelvin. So I guess the red here, it represents the distance between bromine and hydrogen. So as we can see, okay, so first the blue is the distance between carbon and nitrogen. So the first event is the breaking of nitrogen and carbon bond. So roughly about 200 or 100 femtosecond, we see the breaking of the carbon-nitrogen bond. And as time goes by, this distance becomes ridiculous. And at around maybe 800 femtosecond, we see the formation of hydrogen bromide. And actually this hydrogen bromide bond is quite stable because we can see this is the oscillation with time. This is the signature of stable chemical bond.
Yep. Total energy before and after, if you optimize the reactant and product, which is more stable? Can one tell that it is exothermic and product is more stable?
Yeah, can check that. So finally, around 1200 femtoseconds, we can see the fatal group is not attached to the silicon surface. And also, because this is high temperature calculations, so there is lots of kinetic energy in the system. So we see the reconstruction of the surface.
High temperature means how much?
2000 Kelvin.
2000 Kelvin.
Yeah.
Okay. Yeah, so this is bulk silicon, right? Silicon 111.
Yeah.
Yeah, I know that it around something 1100 degrees Celsius. I'm sorry, 800 to 1000 degrees Celsius. silicon 111 reconstructed, and the structure is completely different. I'm not sure that is applicable here. If that is applicable, then what would be the position of that functional group? Like in which atom or somewhere else?
Yeah, we see some reconstruction over the surface. Like here, we see the breaking of silicon-silicon bond, right? And also there is some hydrogen migration. The reason we cannot see any change because we fix the atom of the silicon for
So
AID
is it clear which kind of reconstruction? Is it 7 by 7 or?
Let me bring up, I need to serve as a translator.
Okay.
It's a very colloquial language. So, in surface chemistry, for surfaces without hydrogen, which may dissolve thermally, the diamond-like structure of silicon is reconstructed, not arbitrarily, but in high symmetry pattern, periodic pattern on the surface. The period of the surface unit cell is so much bigger than the unit cell that we use in these simulations. What Fatima is mentioning, she's the best expert in the room and probably on the whole university. It is like 7 by 7 unit cells. To reproduce this, the word reconstruction when she is using means not arbitrary reconstruction deviating from crystalline, but it is highly periodic. And let me translate. Her question is like, would it be reasonable for higher temperatures to start not from crystalline covered by hydrogen, but from so-called reconstructed surface? We cannot do it. It will be extremely expensive computationally, but it's a good point to address.
Yeah.
Am I translating, Fatima?
Yeah. Yeah.
Possible way, probably we shouldn't change anything in calculation, just keep doing as we do, but bring up some verbal hand-waving argument so that we are ramping up temperature so quickly that there is no time for construction. Or maybe some other intellectual argument. I'm not telling that this one is the best. And maybe Fatima can suggest something. So reconstructions that you are telling about appear after annealing, when you heat up and then cool down and keep it in vacuum.
Yeah,
right? And if there is if it will be residual hydrogen around, it will distort this reconstruction back to this hydrogen termination.
Yeah.
So
what happens if it is 7 by 7 reconstruction? Then there are two sides, one faulted side and unfaulted side, and there are 6 atoms. That atoms, 6 atoms on each side, and each atom has one dangling. So this functional group can occupy one of the dangling points. I'm not sure. I'm just.
What's the time scale for this kind of reconstruction?
Time scale?
Yeah.
Time scale, I don't know.
days or hours. So it's it doesn't mean immediate implications. Maybe another paper start the same simulation from reconstructed surface.
Oh, time means just I applied direct heating through direct current, and right away it comes. Oh no! After applying heat, I was waiting like 30 minutes, and then I checked the surface. I saw.
Okay, here we're speaking about like femtoseconds, picoseconds. It will not happen at this time.
And also, so if you have the...
I'm sure something will happen. Probably not like a very nice surface, but positions must be changed.
Yes, but he already like alluded that part of it is frozen. So only the top atoms.
Surface. Because the surface atoms have dangling bonds, so they will be constructed.
I thought there's hydrogen on the surface.
Yes,
Yes.
we have a hydrogen surface.
Yes.
Where does the bromine come from? Sorry. I'm just looking at the reaction scheme they showed in the first slide, and I don't know where bromine's from.
Just part of this kind of a molecule.
Oh, it's part of the
Bromine is
molecule.
negatively charged, and the
It's
molecule is
boron,
positively
not-
charged.
Boron. Isn't it boron?
Is bro? Is
No,
boron?
no, no.
Brilliant on this page.
I thought boron was
on
BB.
the first page.
Oh, yeah.
It should be bromine, halogen, like under chlorine in the periodic table.
Oh.
Right? Fluorine,
I know
chlorine,
what
bromine.
boron. Yeah.
But he's just saying they used BF4 in the first one. The
So it's
boron-
different experimental setup.
Wait.
The first page is from the paper. The only difference is,
So the paper says
Anion.
boron, tetrafluoride.
yes, but you can choose whatever anion you want. It will.
Yeah, so it's
won't
different
affect-
experimental setup
Yeah.
than the first page.
Yeah, we are missing
color.
brain weight here. The schedule was scrambled. I didn't send additional invitation. There is a project that a lot of you may witnessed or participated, that this functional group, this compound of the diazonium salt, is actively used to functionalize carbon materials like carbon nanotubes. And one of the discoveries that Yulun is presenting right now, that this functional group is really able to influence in positive sense properties not only of carbon nanotubes but other materials as well. So in some sense it is not, well, from one of the angles, it's not study of silicon, it's more study of the diazonium salt as it can functionalize other materials.
What'd you call the salt? Sorry.
Huh?
What'd you say the salt was? Sorry, diazonium.
Diazonium. So if you see what Yulun is showing, it's phenyl benzene ring connected to two nitrogens.
Uh-huh.
And if you construct it this way, it will be charged.
Charge.
And in order to compensate charge, you need additional anion. So this cation is anion, so it is a salt. And when you try to evaporate, sublime, deposit, it decomposes and actively tries to bring phenyl group to anything.
So can you call it like a Zwitter ion, I guess, or no?
Zwitterine should probably have two tails.
Oh,
which are
tails. Yeah, that's right.
Far
That's
enough from each other.
Yeah. Okay. Thank you.
Yeah, it's not 10 minutes.
So just we have observed the functionalization of phenyl group on the surface. So next time I just want to compare how much the electronic structure can be changed by the surface functionalization. So I create four models. This is surface is passivated by hydrogen only by one phenyl group. And then this one, half of the surface is passivated by the phenyl group. And here, all surface atom is passivated. So this is the sensitive states. So this is for hydrogen only. This is for one surface ligand, half surface ligand, and the fully passivated. So as we can see, the top three looks very similar. But I guess the biggest difference is for the fully passivated surface, especially in the HOMO, I guess. So we can see the contribution from carbon.
So did you plot this directly from the outcar, or did you shift it at all?
And shifted it.
You shifted?
Yeah.
So where's your homolumo gap?
So for this one, for top three, it's about 0.7 electron volts.
Okay.
For this one, it's like 0.45, something like that.
Okay. So the top three are open and the bottom one is kind of getting close.
Yeah. I guess one reason is because the phenyl group is kind of bulky, so there might be some reconstruction on the surface, and also there might be some hyperstacking. And this is water spectrum.
So in spite of the almost closed gap, the absorption is in the silicon-silicon transitions.
Yeah.
So this phenyl group do not contribute to absorption.
They might be optically inactive.
Very good, I guess.
When you
Others
do
there is some.
carbon nanotubes, do they see a change in absorption as well?
A lot.
Oh.
It's a whole business, and the whole, well, not whole, but half of doctoral thesis of Brandon Gifford.
I thought that was emission.
Absorption as well. So there are additional transitions, optically active transitions due to this group. And the transitions for, I'm not sure if an analogy is possible, but nature of transitions is not involve this phenyl group, but it localizes the bulk states near this group and changes the transition energy.
Okay, I guess this is my last slide. I guess in future, I will do some non-adiabatic couplings for these models.
Okay. Why surface? Why not quantum dot or nanowire?
I guess from the point of view of starting chemical reaction surfaces, it's much easier.
Okay, so it's just a question of how easy, but from point of view of applications, if one is looking to, well, right now the interest was only in reaction, but if you look forward to applications and possible change of electronic and optical properties, would they be more proclaimed, declared on the nanowires or quantum dots?
Yeah.
And maybe there should be like experimental works on spectra for the new functionalized quantum dots or new functionalized nanowires. By the way, then one can combine this project with nanowires project, and electronic states localized on the phenyl will have no dispersion, will be like flat, and silicon states will have dispersion. I don't know, it's just a fantasy, but far future. Okay, but let's thank Yulun. Is anyone else coming?
I'm not sure.
Okay, then we can hold you.
Okay, I'll hold.
Okay.
You want me to go?
Yeah. Because what Fatima is going to present will be definitely longer. It will be a dessert at the end of our meeting lunch. One needs to come with a screwdriver.
Yeah.
It could be open, yeah.
Okay. So, what I am currently trying to look at is the effects of an electric field on like a full perovskite solar cell. So we've got a electron transport material, which is a titanium dioxide, and a hole transport material, which in this case is spirometad. And so it's just kind of a first level approximation, I guess what we're doing is, I already have the ground state calculated for this for like a spinless system and a non-collinear spin system. So this would be the, just bare bones, ground state stuff for the spinless system. So let's see. So I guess this plot here is showing the projected electron occupation, I guess, sorted by the orbitals. So like each one of these is a different orbital, and this is showing you the occupation projected onto the z-axis. So, kind of going through the solar cell. And so there's these lines kind of drawn in here to kind of show you, whether or not it's localized on the perovskite or on the spirometad or on the titanium dioxide. And so, just as so I guess the main thing we're trying to look at here, what's that?
Which one is the homo and lomo band?
Homo lumo.
Oh, pure.
Yeah. And then, over here, that's these guys and then these ones.
Oh.
So I guess the main effect that we're looking at is the energetic reorganization of the band structure due to the electric field. And then, so that's really what this is showing here. I mean, we're not looking at any of the other effects that the electric field will have just yet. I'm still trying to collect data, and VASP is not wanting me to do that. So what we did here is we took this data, and then we averaged it out to figure out, where the expectation value for the electron position would be in each orbital, and so that's what these dots are all representing. So blue is with no electric field turned on.
Can I play a picky joke?
Sure.
What was the goal? What was the motivation to launch the studies?
So when solar cells are actually used, they're going to be connected together so that you can create, larger voltage than any one solar cell will be able to produce on its own. And so that is going to create an intrinsic electric field that will be acting on the solar cell. And so we're essentially looking at how we could sort of tune that to get the, I guess, maximum performance out of like a solar panel.
So I have a question off of that.
Yep.
Would this effect be seen if you only had a single cell in your solar? Like if you take one cell out, would you still see electric field as it has a load on it? Or is it intrinsic to taking a ton of them together and then having a device, or is it intrinsic to the architecture in and of itself?
Should be definitely predominantly due to the architecture. Let's see whether or not there is any in the other cases. I would think that if you had a singular solar cell, you could design it in such a way that you wouldn't really have an electric field acting on it if it was just that one cell while it was operating.
Charge separation. So
you'd
always
have
have
one
an
electron's worth, I guess.
Right. So it's.
But you should be able to, as soon as that escapes, you could theoretically design it so that there's no more electric field acting on the solar cell.
To do that is harder than
right
to say. So this is kind of studying the intrinsic effects of splitting a charge, like make a positive and negative charge carrier.
Mm-hmm.
What will it do? And if it does stuff bad, then you can propose how to fix it.
Yeah, essentially.
Okay.
So what was I talking about?
Technical details.
Yeah. So with these, what we're doing is we're, averaging out the position of the electron in the z dimension here, and then we're looking at how the electric field reorganizes the orbitals energetically speaking, I guess. I don't know, should I?
So what's the
talk about how-
Hamiltonian of field to matter interaction?
What's that?
What is the Hamiltonian of field to matter interaction?
You just want me to like write the equation, I guess?
You can write the equation, or you can just quickly tell 1 or 2 words.
We're basically treating it kind of like a dipole. So if the average position is somewhere over here, then it will shift the energy up with a positive field, and if it's somewhere over here, it will shift the energy down with an electric field, and vice versa, I guess. But
So
like
field to matter interaction are considered in dipole approximation.
yes. Yeah, so the farther away it is from the center, the more dramatic the effect of the electric field will be on that orbital. Which, yeah, you look like you have kind of the same issues as I do with that. I guess it's kind of a...
Where, isn't it periodic? So then-
yes.
Why would you say the center of your cell?
So it's periodic.
Because you can just shift your cell and then your center changes,
Yeah.
then the effect goes away.
Yeah. So, okay, so it's periodic, you know, like, as it's shown here, like up and down and then in and out of the screen. I mean, it's technically also periodic, you know, left and right, but there's more vacuum that way. So the effects from up here shouldn't be having an impact down here. I mean, we're cutting it a little bit close, but I mean, for the
You
most part.
have like 10 angstroms between if you go from one end to the other. Because you're about 5 angstroms when you first see your first peak,
Yeah.
and then you go to like 35, so it's about 10, right?
Yeah, somewhere in there. I mean, yeah, so that's, I guess, what I have at the moment for that. And then if you look at the non-collinear spin, qualitatively it looks about the same. I mean, you know, you're not getting any drastic changes that are just jumping out of nowhere with this. So, yeah, I guess I don't know if there's really too much to talk about with this at the moment, but I was able to get non-collinear spin to work for the ground state, at least so far. I was just toying around with it, I guess, and I figured out where the HOMO and the LUMO would actually cross, like where that electric field threshold would be. And so that's what I plotted here in the spinless case. I don't know, just it seemed like a good point to plot. I guess I don't really have anything to talk about too much with this at the moment. I mean, I'm still trying to actually get some meaningful data. And then same thing in the non-collinear spin case. You kind of get more exaggerated effects, I guess. But I mean, again, it's still in too early of a stage to really make any like actual claims on this. I tried to make a movie of my molecular dynamics runs that are failing to see if any of you knows how to fix this. So essentially the perovskite is just frozen in place every time I try to do molecular dynamics, and then these two are, you know, doing stuff and then they just go crazy. And
So they disattaching or what?
yeah, they end up like shooting through the boundaries, and that's weird. Cause like it should turn into a horrible mess right at the end. Huh. I mean, you can kind of see it starting to right along here, but basically my MD runs all look like this no matter how I try to do it, where, you know, the HTM and the ETM are both, you know, acting like they're at the appropriate temperature, but the perovskite is essentially frozen. And then they'll end up just wigging out and going through the periodic boundaries.
Just not moving very much or what?
It does move a little bit.
So you run this calculation for all atoms moving.
Yes.
Right? You not freeze, because you can
Right.
freeze some atoms.
Right, but I'm not trying to do that. And I mean, these are all significantly heavier atoms than, you know, the ones that are appearing here and here. So they should move less, but
What temperature are you starting them at?
so I'm running the molecular dynamics at 300 Kelvin.
So when
Around
you did
100.
your heating,
What's that?
when you heated
Yeah,
your system, what was your beginning temperature?
0.
And then 300 was the end.
Yeah. So I go 0 to 300, and then I try to run MD at 300,
Did
and
you-
MD is where it wigs out.
Did you do like stabilization period? Because depending on how your input is, if you start at 0 and end at 300,
Yeah.
it will slowly increase the energy.
Right, yeah, that's what happens. The
Proportional to the
temperature just
mass.
keeps going up and up and up in the MD.
But then if you stop at 300, it's not actually equilibrated to 300.
So you're
then,
saying do
then
like,
you need to do a second calculation typically.
yeah,
Start at 300, end at 300,
another heating one?
so that,
Okay,
because if you, in the beginning, it would do this.
yeah,
And then at the end, it should have like an envelope function
Mhm.
to like get close to 300.
yeah,
So it might be that your initial conditions have all the kinetic energy in the light elements,
yeah,
and your heavy elements have not really been able to equilibrate to 300 K. 300
okay,
K.
yeah, because I haven't tried to do a separate heating job at
Yeah.
300 degrees. I've tried to like increase the length and, you know, like send it back in from an MD job and,
Yeah, if you increase the
That
length,
doesn't
it
seem to be
just
working.
heats it slower.
right, yeah,
Or that's what I found. It depends on your settings,
Mhm.
but I think if you take the one from Dimitri's bin, it takes the number of steps
yeah,
times however, like the amount you need to move, and does a linear
Yeah, it's like-
change.
yeah, it's every NSW, or every N block steps, it'll give it a thermal kick
Yeah,
over
but
the,
it
you know,
does it
equally
linearly.
divided over the NSW steps.
But here is a conceptual problem when you deal with this kind of systems, right? Because you have so big difference between vibrational frequencies of your organic molecules versus inorganic molecules.
Yeah.
Those solid ones, right? But when you apply classical heating means classical thermodynamics, right? You're kind of thinking that you put this energy
Mhm.
kT with your whatever temperature equally distributed over all degrees of freedom, over all frequencies,
Yeah.
right? But we understand that those which are solid one, right? So for them, this classical approach is okay,
Mhm.
but the soft guys, they actually should be treated quantumly.
Okay.
And kind of, in other words, this energy should not be equally distributed over all atoms.
Is there a way for me to do that in VASP?
No, there's no way.
Okay.
Nothing
Yeah.
in calculation. So
I'm saying there is a
It's
conceptual
just kind of,
problem
yeah.
with this approach because you put in a classical limit you kind of take your energy, divide it over number of atoms, right? And this would be roughly over oscillators. And roughly speaking, the average energy for each oscillator would be this amount, right?
Yeah.
But in reality, this approach will be applicable only for your middle part.
Yeah.
And for the other ones, they should actually get only the energy equals to their h nu, which should be in a level of 1000 something 500, which is much lower than kT, right? So it means you should not really add any energy to the soft atoms at that conditions because they can get only this quantized energy, not classical way.
Yeah.
But because you treat them equally, that's probably makes kind of oversaturating the energy to this, like you put like real energy which your organic molecules get is not really 300 K, right? It's, if you recalculate, then it would be much bigger, and that actually causes the breaking of the bonds.
Okay.
So the question, practical question, can we do something in the past with this? I don't know, technically.
Not that I'm aware of.
Another way you can, or you can
freeze
do,
organics.
you can
Yeah,
make
organics,
tricks.
yeah.
You can make tricks, freeze some molecules,
heat everything.
then heat the
And
guy.
And then during molecular dynamics, unfreeze. So
Yeah.
let heat slowly dissipate from semiconductor to organics.
Or you can freeze everything except the carbons which are really involved in a connection.
Mhm.
I mean, freeze organic without carbons or whatever, oxygens or whatever are getting into the coordinated bonds, right? Connecting with your surface. So they can adjust a little bit. And then maybe freeze all other guys and let only organic to move and see what happens.
Yeah.
But something creative has to be done.
Yeah.
I would try and heat it for a long time with initial and final at the same temperature.
Okay. Yeah.
Because what might be happening is, as Fatima was saying, you might not put any energy into the perovskite.
Well, right. That's what it looks like is happening, and I guess I just wasn't, because like I've tried to just kick up the time. I figured that was the obvious solution to that is just let it run for longer.
Because once you get an MD, it's not monitoring the temperature anymore.
Right. And every time it just starts to go crazy on me. Like it just goes up and up and up. That's I don't really have much in the way of data right now. I'm still trying to get things to work. So that's all I got.
Okay. Good thing, Landon.
So as Dimitri was talking earlier, this is part of a competition tomorrow for a travel grant. This year they have 2 $500 travel grants and then 2 $300 travel grants. And this is what.
And no 500?
2 500,
Oh.
2 300.
Oh, I see.
And I think there's only 6 of us competing, so hopefully I come back with good news instead of I'm in the bottom of the
could say.
So this is,
So 6 and you get 4 awards,
Yeah.
right?
yeah,
It's a good chance, but you never, well, I would say you never know.
you never know.
How many minutes? How many minutes?
15.
Ooh, so and it's sharp, right, with questions,
I think it's 5 minutes after with questions, like 15
and 5.
done and then 5.
Okay.
And then this is their judging criteria. I just put it up so that you guys would have some background on what I should talk about instead of just give a presentation and then, yeah. Oh, that's gonna. So today I'm going to talk about computational insights into the manipulation of the ground in the excited state of iridium complexes via benzoanylation. Just to get off, I kind of want to explain what benzoanylation means. It is a fancy word to say extend the pi conjugation of a system, which we were talking. I'll show an example shortly. But before I get into the nitty-gritty of my research, I would like to go over some background and get some motivation. So let's look at some applications of iridium-3 organometallic complexes. So I'm sure everyone has heard about these because most applications are very widespread. So the first is for lighting, organic light-emitting diodes. Here's an example of architecture of it, and this portion here is where the iridium complex sits, and that is what emits the light. All the rest of this is to have charge carriers be injected, and then they can recombine on the iridium complexes. Here's an example. So this is from a paper, and they're trying to tune properties of the organometallic complex to make their light-emitting diodes perform better. And what they did did functionalization with fluorine and methoxy to try and tune the emittive where they emit. The next application is low power upconversion converters. So this is an application where when you shine light, we want to have the emission above the light absorbed. And here is an example of it. So you have a green light, and then when you have the upconverter, it turns blue, which means that your emittive state is above the absorption state. And the last application is biolabeling. And here we see an example where they inject the compound, and then it spreads throughout the body through the vascular system, and it gives the contrast between different organs so that you can do studies to see what's going on. With all of these, there are some complications. I'm going to talk about the first and last. The first complication is that LEDs, for most applications, if you want red, green, blue, you need to have Gaussian or Lorentzian emission spectra, which is why a lot of people think about quantum dots for light-emitting diodes, because they're very pure in their states. So we don't get a lot of tails if you have ideal ones. For with organic compounds, you tend to have a lot broader lines, which I kind of had in the back. You get like vibronic peaks, which is one problem for organic light-emitting diodes. And then for the biolabeling, when you have skin, if I have my skin up like this, you can't see through it to this wall because light is absorbed or reflected. which means if we use organic iridium complexes, we need to have emission below around 800 nanometers, which then can penetrate into the skin for imaging purposes. What I'm going to talk about.
So this is infrared range, right?
Yes.
Already 800 is infrared, right?
Yes, it's near infrared. Through this, we have our application and challenges. How can we resolve some of these challenges? I'm a computational chemist, so we can take the organic compounds and try and manipulate the structure. And in literature, there's two predominant features of this. It is functionalizing the coordinating ligands with electron donating or withdrawing, and this is typically inductive effects, which are like flowing tetrafluorine methane attached, or like amine. So that's one way. The other way that I'll be focusing on is extending the pi conjugation, or as I stated before, benzoanylation. And here's an example where we add pi systems onto a parent structure to make new structures, and then you can study these. So you can do this either experimentally or theoretically. I am a computational guy, so I'll be studying it through computational chemistry. And why is this advantageous over the typical what chemistry? Well, computational chemistry, you can do high throughput, which means you can study hundreds or maybe even thousands of compounds that are potential to narrow them down to a handful that you can then have an experimental collaborator look at through actual studies and say, oh, these are decent, these half are not so decent, but we have better candidates. And DFT, which is the theory that we use to simulate these, can give us atomistic properties that then we can have in the back of our heads and say, we want to use these properties in the next generation of compounds. So now I'll be starting the main part of my talk, where we have 3 studies where we do benzoanylation. The first is on the diamine, typically the NN ligand. So we focus on modifying this where the CN is kept the same, and we want to see what happens with the benzoanylation. So you've seen this before, and what this is describing is the splitting between the parent compound and the 1,3-dibutene, where the symmetry of the HOMO and LUMO is just looked at to describe if the HOMO of the compound that's being benzoanylated either go up or go down, which then would dictate the HOMO-LUMO gap. Let's look at this in a little bit more detail. Forgive me for the blurriness, but here we are extending this portion, and there's no angular node here, which means the state that will couple is the LUMO, and due to a LUMO-LUMO, the new state will be lower in energy, which will decrease the HOMO-LUMO gap, which is seen here. So from 1 to 5, it decreases the HOMO-LUMO gap. The one problem with benzoanylation somewhat is if you extend it too much, you change the character completely. If we look between compound 1 and 6, we put benzoanylation here and here, which this has now a large pi conjugation system, and that changes the emission character from a charge transfer, which means the hole and the electron are located on different parts of the molecule, goes now into a pi star, and you can see a dramatic change in the emission property, which this may not be bad for bioimaging, but it would be bad for light emitting diodes because you do not have pure light. So from this, I would like to go on to the second study where we look at the C10 ligand. And from this study and the first study, we come up with very similar conclusions theoretically. When you do a homo -1, you increase the energy. When you do homo, you also increase the energy because you never make a state in between two states that you're coupling unless you have a third state. And we can predict this for all of them. And from the emission, we also see that for 8 and 10, when the pi conjugation system is very large, it emits with pi star, not charge transfer, which is kind of supporting the idea if you go past 3 linear benzene rings, you're going to probably have a charge transfer state. And from this, I'll talk about the last paper that I'll be discussing, where we did benzoynylation on the NN ligand again, and the results are very similar to the first 2 papers. So I will not belabor the point too much. And here we can say we can tune the homo-lumo gap by about 1/2 of the electron volt, which is pretty dramatic for organic materials because unlike quantum dots, where they're size dependent, a lot of these properties come from the conductivity. So benzoynylation is a good tool to tune your homo-lumo gap and in turn your absorption and your emission. And here we see for a 3 linear system again, we have another pi star transition. With that, I would like to conclude. Benzoynylation, I didn't show absorption much due to the time constraints, but benzoynylation can modify the frontier molecular orbitals, which then in turn modify the absorption and emission. The site of benzoynylation really determines how. So as a computational chemist, I can take a parent molecule, run VFT calculations, go back to the experimentalists and say, these are good points for benzoynylation because the energies will go down, which is what we're kind of looking for. We want to go under 800 nanometers. And then the last is if you have too much pi conjugation extension, you'll go from a charge transfer to a pi star. And finally, future work, we can take the compounds that we've already studied and jumble the C10 ligands with the NN ligands and get even more combinations so that we don't have to come up with, experimentalists don't have to come up with new routes to make ligands. They can just take the Legos that they already have and mix them in new ways to try and make new compounds. And then the last is introducing spin-orbit coupling so that we can see the actual oscillator strength to go from the excited state down to the ground state. With that, I would like to thank my group, my advisor, which is a co-author, Brennan Gifford, Javed, Dr. Soon, and Bing Ching, which is also a co-author, and then for the computational resources, NDSU CCAST.
How many minutes?
whoopsies.
Anyone was monitoring time?
It was very
No
quick.
one?
Was it less than 15?
I wasn't
Okay.
exactly measuring, but it was about right or even shorter.
Okay.
It's recorded, so.
Oh, that is
Figure out
true.
what-
I can. Yes.
So you found that benzoynylation has some effect on the absolute emissions, but how long you can extend this to change this, tuning this emission properties? Is there any limiting case or anything?
So, if you're talking about experimental results, I would say if you are if you're putting like 5 rings on it, it would probably be better to find a different parent molecule that has properties closer to what you want than to keep adding rings, because the more carbon you have, typically the more costly your system becomes. So for us, it's
Is
not.
just cost, or what about from the properties for cost?
So as I said, I've found that if you have 3 benzene rings together, or if there might be a nitrogen in it, then it will probably be a pi-pi star transition. So if you have even more carbon, I would assume it would still stay a pi-pi star.
Why is it a problem? Oh, so what? Let's it be pi to pi
Yeah.
transition. Why it should be charge transfer state? What
So
kind of physical benefits it gives either having this type or
So
that type?
charge transfer tends to have a longer lifetime in the excited state, so that if you have pi-pi star, they won't be as good as like non-linear optics, which is another reason why we study these compounds. So lifetime is also important. And when I showed emission, they were always normalized. So like all of these are normalized. And if you notice here, this is very smooth, where this is pretty jagged. So you could also play with the how bright the compounds are. So if you have a very long system, that may have more pathways for non-radiative relaxation, which then is not what you want in the applications that I was talking about.
So you mean long means more than 3?
Yeah. But if an experimentalist says, I want to do 4, that's up to them. Yes.
Question. Who is your target people are you gonna be hitting with this? Like, are they, well, I guess my question is, how scientifically knowledgeable are those people?
Which people?
The judges who he's
Oh, the
presenting this to?
judges.
So I know
Should be
one's
faculty members
From
NDSU,
Alex Parent, and then
from
one's from Mayville, and I think one's from Grand Forks.
yeah. So they have faculty from different universities,
Oh, okay.
which are in
so-
our neighborhood.
In the scientific community, not in
Yeah, it's
You won't have,
It
like,
is
philosophers.
scientific presentation for kind of focus that this will be presented to ACS conference. So it's definitely aligned to the professionals rather
Yeah.
than just broad audience.
and
Okay.
I could try and bring more flowery things to it. I just have a lot to go through in 15 minutes.
Yeah.
So to add even more,
Now, I would just say that, like, if it was just for a more general knowledge, maybe just the introduction, try to
yeah,
capture those people, because by the halfway through your talk, they'll probably be on their phones or
yeah. So
thinking elsewhere.
I might try and reduce the technical jargon, because the 3 studies computationally have very similar results. Experimentally, they're different, which is why they're in different papers, but the 3 main results are in every paper, so I tried to hit home that.
Okay. No, but it still seems like there's people that are well knowledgeable in the scientific community that are going to be going there, so it's not a bad thing.
So you said that 3 papers only different because you say experimentally. I take it as synthesis is different, or what is really different from experimental point of
So
view?
the results experimentally, so the which compounds have higher excited state absorption, which means like nonlinear optics.
Higher excited state absorption. You mean higher, larger energy, or what do you mean higher? Or more
No,
intense?
so transient absorption
Ah.
can be different. And the routes to synthesize these are different. I have
But my question is,
like how to do it, because I don't want to
no, I don't want you
Okay.
to explain how they were synthesizing it. But my question is, you said that you increase benzoionization, and in all cases when you increase its redshifts, does it also deal with position where you do it?
be. Yes, and that's
In
why.
and I guess there's also probably different difference in these papers, right? It's not just the length of these molecules; it's also their position in the
Yes.
ligands, right?
So that was this point. Maybe I didn't drive it home enough, but the site of benzoinylation determines the interaction. So if it's a homo-homo transition, then it will decrease the homo-lumo gap. If it's a homo-lumo transition, it will increase, or vice versa.
Well, again, when you say increase interaction, it's
oh yeah, that's
it's
not,
kind of
that's not
inside, right?
Yeah.
But your output, that because of this change in interaction, you will have difference in the energy of the optical transition. Then it's a little bit different focus for this point. And can you return back to your slides where you're explaining what's really causing these redshifts? You were addressing this in 2 slides, I guess.
6, 7, I guess.
Here?
Yeah, one. I think this was, yeah, but this will good. So you were talking about something luma luma homa homa, and I didn't really get what exactly luma luma homa homa. What's really this dashed lines mean?
So here, if we go to the full size, it's a bit hard to see, and that's why I blew it up. If we look here, there's an angular, there's a node here, which means that
Well,
one phase is here.
First of all, what exactly are you showing on these smaller bubbles?
This?
No, that, no,
Okay,
what is that?
the big guys, this is your complex,
Yes.
and
So-
the small one is what? It's
Yeah.
just a ligand, right?
Yes, the 1,3-di.
You just take isolated ligand,
Mhm.
which having this how it calls, where you increase your conjugation, or what kind of ligand you look at? There are
So
several
this-
ligands in your molecule, right?
So this ligand, so
Just
we
go to
have,
your structure.
Beta
Go to your
E
structure.
is your-
so we use this.
But can you go to your structure? Because you having 5, 6, or how many complexes, right?
Yes.
Where you do the change in just this ligand.
Yes.
So then, which exactly ligand
So
we're
if
talking
we
about?
look at 1 and 5, right? This is what is new.
Mhm.
So if we take 1,3-dibutylene, which is this compound with instead of having it connected here and here to the carbons, you put in hydrogen. So we have a hydrogen here and a hydrogen here, here, and then this group. So we take this, we take that group, and we say, how do the frontier molecular orbitals match? So if this position here has a node, then the state that will interact will also have a node. If the lobe is centered here, then the homo or lumo that has no angular node will interact, right? So we can say here or
Here.
there, but these have different phase. So let's say this is positive, this is negative, correct? Then if this here has a node, then it will interact with that state. If it does not have a node, it will interact with another state.
You mean having a node in a molecule, in an actual
Yes. So if we look here,
combined structure?
this is 1, this is 5. This is where we're growing, right? So now there is no node here. It's 1 electron density. So there's no change in phase. If we look here and exclude the outer portion, it stays red the entire time. So there's no angular node, which means that this state will interact with this state. It will not interact with this state because the symmetry is not, it doesn't match. So it can't interact, which is why this is a lumo-lumo interaction. And lumo-lumo forces the new state to go below the old homo. So that's why it goes down by about 0.2 eV.
The problem is that it's completely unclear when you explain and spend like another 15 minutes on explaining this thing.
Okay.
I think it's kind of people can get it. But it was completely unclear what's exactly going on and what the small features are
Okay.
and why they should have luma kind of interaction, right? Is completely, I don't know. For people who were never doing it, probably you never really
Yes, and I
get
think,
what's exactly going on, right?
so do you think adding a slide between why study computation and the studies where I show the interaction of orbitals
Maybe
would
you
be
can,
helpful?
again, if you think that this is a very important point, right? So you probably can again go to your structure, like say, okay, and now we want to explain what really causing these shifts and why they're not really consistently, because you expect, like, am I right that your conjugation is growing from 1 to 6 if you go complex 1 to 6, so it's not really right. And you kind of think that if, like, just idea, so you increase in the conjugation length, you're supposed to shift it to the red consistently because of the increase in the conjugation, like particle in the box model. But it's not coming consistently, right?
Yes.
So, and moreover, you can say that your HOMA is kind of not affected at all, right?
Correct.
But your LUMA is doing crazy things, going up or down, and down or up, and stuff like this, right? So probably you can go a little bit in the if you really think that this is an important point, you can just look, kind of focus on this overall results, say, well, we see this kind of behavior consistently for HOMA, but not consistent for LUMA. And then the question is why, what's really causing it? We want to answer this question. And for this, we kind of make a model, simplified, artificial, whatever you can say, model of just this piece of the ligand and see how much this, if orbital is, if the electronic density is contributing from this piece, kind of what exactly responsible for changing this HOMA-LUMA. So little bit baby steps, given a general idea what exactly this model is, right? And then you say, and then nodes or whatever, and then overlaps or kind of interaction, whatever you call it, would be facilitated or will not happen. And if it happens, then what happens with your LUMA? If they if they interact, then LUMA is going down, right?
It depends on which states. So if it's LUMO, LUMO goes down.
Yes, but I think this is what you say. In all these cases, it's LUMA, not LUMA-HOMA, right?
No, so this is HOMO-LUMO, and it goes up. That's why this, and this is high.
Okay. Mm-hmm.
Yeah, so there's 4 different cases that can happen.
So again,
Yeah.
it looks like you need refocus this slide, like maybe break it into 2, and again carefully think about timing. And you need extra time to explain it.
Yeah, and I might not go one by one with the studies because they're so repeated that I might like hold.
Yeah, you can just, if this is your central point, you kind of explain this feature, then you can you go to the next series? And then you can just say that changing this ligand to slightly different one, you can call a name, right? Kind of results, like we apply the same methodology and we again see very consistent results for LUMA, HOMA, going up or going down, and that's it. You don't need to go to the details anymore. Okay. The slide can stay the same, but you spend like really a couple of minutes, seconds on it.
Okay. Any other questions? Okay.
Can you go back to your motivation?
Motivation.
I think it was good, but just maybe highlight it a little bit. So you're showing 3 examples, right?
Yes.
And for biological labeling, I think you explained very nicely why is it important. Like your goal is to find such ligands which will move it to the red, right?
Mm-hmm.
But on the other hand, you said that other parameters are important, like lifetime, something else. Maybe again, in your introduction part, you need to add this, saying that We're interested in what specific parameters you are focusing on. So first it's energy, which we want to shift to the red as much as possible to get kind of infrared emission. Lifetime, what else? I don't know, the emission, how it calls, the intensity of emission, right? The cross-section of emission or something like this.
Yeah.
Is it bright or is it, and of course, all the three of how many parameters will be, some of them or all of them will be more beneficial for this application or that application, right? And then you probably can say, we will focus only on a question of the shift of the energy. We're not really considering lifetime release. Or maybe I'm wrong, because if you talk about the change in the charge transfer versus pi character, right? It kind of relates to the explanation of the change in the, you expect that then change in the behavior, change in the nature will change the lifetime, right?
Yes.
So maybe you also can say, and
Okay.
and briefly give some intuitive ideas, or how to say, qualitative ideas on a lifetime with respect to the nature of the orbitals. Kind of narrow down your focus, what exactly your calculations will be focusing on as an outcome, what you need to get as an outcome. Put it into your motivation as kind of narrowing down to very concrete question.
Any other questions?
Okay, well, thank Levi once again. And we have last speaker, but not least in the program, Fatima. You are invited to the stage.
How long you going to talk?
She has like 15 slides.
I will stay for another 50 minutes, and if you will be not done by that time, I will be around.
And maybe
But don't be surprised if I'm leaving, because I really need to run.
if audience is smaller, I'm happy. Less questions, I guess.
It should be like black slide advancing.
Huh?
Oh,
That's
I put it in my pocket. Sorry about that.
So this is my old project. So far I calculated relaxation rate for electron for 2 silicon nanowires grown in 001 and 111 crystallographic direction. Now I calculated relaxation rate for hole and photoluminescence for the same models. Here is the outline. First, I'll talk briefly about the context and challenge, then methods. Method section includes only the procedure what I did, not many equations, not many theories, and then results, and finally conclusion. So we know silicon nanowires exhibit optoelectric properties like band gap, radiative and non-radiative transitions, charge carrier relaxation rates, and all of them are dependent on momentum dispersion along crystal cross direction. Here is the band structure. The reason I showed this band structure because I'll consider only 4K points. So this band structure here there are 16K points, and the next one for first two panels, left panels, there are 4K points only. If we compare the previous band structure and this one, we can see that the shapes of the bands are not changing much. So in order to save computational resources, we consider 4 K points. And the rightmost panel is the valence band of silicon 100 nanowire, and so here is this hole can travel. Since this is valence band, I'm considering hole. So holes can travel from 1 K point to the different K point, or 1 K point to the same K point. If holes travel from 1 K point to the same one, we call momentum restricted transition. And if a hole travel from 1 K point to the different one, then it is momentum unrestricted. I have drawn a couple of them, not all of them. There are many paths here. So, in order to calculate relaxation rate, we need to calculate rate field tensors. As I said, I'm skipping those theories, equations. So, in order to calculate rate field tensors, we need 3 files. Number 1, coupling files, and coupling, since we are considering direct and indirect transitions. So there are 2 kinds of coupling files: coupling between orbitals of same K points, and coupling between states of different K points. I will describe later in details. And number 2, energy of files, it's like symbolic name, but it consists the number of R states we are interested in. And number 3, this is the MATLAB code. So there are 2 names here. And now, actually it should be, this one should be number 2. So this one, this file consists for each K point, we are interested in 80 orbitals. Since we are considering 4 K points, there are 320 orbitals. This is for silicon 100. So here, this is the screenshot how the orbitals are arranging. Here in this bigger file, like which contains all of the orbitals for 4 K points. So here, this is HOMO of K point 4, and right above that, it's HOMO for K point 3, and HOMO for K point 2, HOMO for K point 1, and then HOMO minus 1. On the other hand, this is LUMO for K point 1, K point 2, K point 3, K point 4, then LUMO plus 1 for K point 1, and like it is continuous up to 320 states. For silicon 111, we are interested in 50 orbitals, so total number of states in this bigger file is 200. This number, this one should be number 1. This is right, but previous version. So here we can see the direct couplings of orbitals at same K points. So the format of the coupling file is coupling dot number of K point dot 001, and there are 892 coupling files for each K points for direct couplings. For each K points for indirect couplings, there are another 892 files. So the format of these indirect coupling files are coupling dot K point number of K point 1 to number of K point another one, number of K point 2, and then this is the number of file. So, and the number 3 file was MATLAB code. If we run that code, then we will get this rate field tensor for the same K point for these direct coupling files. And from these indirect coupling files, we can get rate field tensors for one key point to another one. Like our rate field tensor 0.2, k point 2 to 1, k point 3 to 1, 3 to 2, 3 to 4, etc. And so finally, after running the code, we have 16 rate field tensors files here. And we combined all of these 16 here, this 5R file, this super tensor. Now I'm going to tell you how the matrix elements are arranged in this 5R super tensor. Here, this is not exactly the way this matrix elements are arranged. It is a little bit complicated. Like this one is a first element of this one. This is the first element of this one, and this is the first of that one, and that is the first element of this one, and this one is the first element of this one. Now, after first elements are arranged this way, and then the second element of this one is here, and continue. It is continued that way. And this is the first element of this one. This is first element of the field tensor 4.1, and it is continuous. Now, once we have the rate field tensor file, we can calculate the electron and hole dynamics. So for calculating dynamics, we need one more file that is panned out and different MATLAB code. Here it is. So there are 4 files required here. Once all of them we have, we can calculate the electron and hole dynamics. The figure is, I'll show later. I'll put it here, but okay. So once we can calculate the dynamic, electron and hole dynamic, after that we can calculate the photoluminescence. For calculating photoluminescence, we need 5 files. The rate field tensors, that file that contains total number of orbitals, and Formaster optics file, band hour, and this MATLAB code. There should be another one more name here. Okay. Now we need to arrange, since we are considering 4K points, we have 4 Formaster equation, and in order to correlate with the, in order to arrange similar to our the super tensor, rate field super tensor, we arranged our 4 Formaster equations this way, and this is Formaster equation, Formaster file for K.1, and it is diagonal. So Formaster for K.1, Formaster for K.2, 3, 4, and all the other matrix elements are 0.
So are you assuming that there's like no cross interaction, or how can you say everything's 0?
No interaction we are considering.
So what would happen if there was interaction? Is it even possible to have interaction, or is it 0 because it has to be 0?
It, honestly, I don't know.
Can I interrupt? There are no violation of momentum conservation due to interaction with light. So it is assumed that interaction with light, absorption and emission of photon, keeps electrons' momentum. Saves. Although the interaction with phonon may change momentum of electron or hole for both. Right? Fatima? Is it what you are modeling? Right? Yes.
What if you have
So then-
polarized light though?
But this is with phonons, right? Since
This,
otherwise it's 0.
what she's showing right now is interaction with photons.
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 So
And what she
but
showed before was interaction with phonons.
you can have a spin flip.
Wait. No spin here.
That's what we
Oh, sorry.
okay.
Oh yeah, never mind. Yes, okay.
So
You
angular
can flip
momentum of
and
photon deal with momentum of crystal.
Okay.
Okay.
So then you are saying by your formalism that it's an instantaneous jump, and then it lets the crystal move, and then if it jumps again, it's an instantaneous jump, and then it lets it move.
Okay, this is the results, relaxation time of electrons. This one is for silicon 100 and this is for 111. This result is published already.
Sorry,
Wait,
can you
what was-
return back to your matrix?
For
Previous
methods. This one?
Okay, so it's 4 by 4 because you have 4 by 4 key points, right? I mean, you have 4 key
Actually,
points.
this is not just 10 here. This is 320 by 320 matrix.
Yeah, so the
Yeah.
zeros are zero matrix.
Zero
that
means
are the
is
same
like,
size.
like zeros until it is 320. So this is 80 by 80
I
and rest
see.
of them are zero.
And what is dictating the size of these matrices? I probably
Because
missed it.
it should be, it should have same dimension with this, like this one. This is 320 by 320. In order to run the code.
And you're getting the 320 again?
Because
How you calculate it with your 4
Because
key
we are
points?
considering 4 key points. For each key points, we have 80.
Okay.
So 80 times 4, 320.
Is a combination of all.
And why is it
different
80 for each key point?
That's the
We
number
are
of states
interested
you're
to
in.
80.
Oh, okay. So you also have limits
Yeah.
for states which you consider.
Window.
Yeah,
Uh-huh.
Same as we all do.
yeah, certain number
Makes sense,
above,
okay.
below comma or something like that. So this is 0 means not only 10.
No, I understand.
80 means until 320 it's 0.
So then what is, you talked about this and then you jumped, what am I supposed to get from that? No,
Which-
not the,
From which
the
one?
next slide.
This one?
Yeah, you were talking about this and then you went to the next slide. What am I supposed to get from this?
Oh, this is,
No, she did.
Yes, answering the
Combine
question.
now.
No, she talked about this and then she went to the next slide.
Oh, because it's the same idea, I guess, right?
Oh, okay.
I'll go to the next
Are
slide.
you now combining,
Okay, do
combining?
you have any particular question here? Like, do I need to explain or what?
I don't know what you're,
But your relaxation time, it's actually based on you're kind of combining two things together now, right? So you have interaction between photons, interaction with a photon, and you have interaction with phonons
Mhm.
together, right?
Mhm.
In these different key points.
Here it means like so this is the dynamic calculation procedure. If we run this code, we get the relaxation rate.
yes. My,
And-
my question's not
And this
what are you doing, it's
Mhm.
what is the result? Because you went to this slide and then you went to the next slide.
Maybe the objection is correct, but what is the next slide?
It's another thing like this.
And what is the title of the next slide?
I
No,
don't
I see
know.
the unit. So,
So let's check. What's the difference?
One is electron and another is hole.
But this doesn't have any lines on it.
I didn't fit
Because holes didn't deserve to have lines.
I need to fit them like
Oh,
these
okay.
are fitted lines here, but this should be. I should
See, it's hard to connect them with lines.
because this is previous results. It's like I did last summer, and it is already published. I just put it here to show the electron relaxation time.
So then it looks like there's a threshold of dispersion energy and then it changes the rate at which it relaxes, right?
Mhm.
Because
Yeah.
like the red line, the red empty square up until like 0.15.
Okay. So what is this? Like this is all means I mean momentum restricted plus momentum unrestricted. So one key point to one key point into one key point to another key point transition.
Okay.
So one is
all-
with same K
all
and
means
another with a crossing.
all means same plus
Crossing.
different
Mhm.
total. And this momentum restricted means just same 1 K point. So these empty symbols are for momentum restricted for only K point to K point transition.
Did we see this result sometime
Yeah.
last semester, right? The
Mhm.
same? So they're the same.
Yeah. Yes.
Okay.
And these are for all transitions, like momentum restricted plus unrestricted.
So with
So the
all momentums,
Mhm.
the relaxing time is about the same.
So if we consider all transition momentum restricted plus unrestricted, then electron relaxes faster.
But wasn't the discussion last semester that it
Yeah.
might be artifact because you're really including more pathways?
Artifact, there was a question
Or
about
maybe
normalization.
the question was, yeah, artifact or not artifact?
Yeah.
Was it normalized? Should it be normalized or not?
Yeah.
Was it this addressed already
Yeah.
or not?
Not yet.
Not yet?
No, it is not addressed yet.
Okay.
Any questions? Yes. I think that's a complicated way to.
Yeah, last semester I taught during this time.
Yeah,
So I
this is
didn't.
last semester, but
I
this
didn't
is this
see
semester.
this.
This is for whole, I calculated, this is recent data. The same thing with whole.
So now lifetime is the trends are flipped.
No, actually the symbols are flipped here. I'm sorry.
Oh, okay. Okay, that.
Compared to previous one, the symbols are flipped.
But
That's why you are
oh
thinking,
yeah,
this is all transition. You know,
Okay.
so also relaxes faster.
I don't have a question. I'll write it down, but it could be very logical to rearrange
Yeah, I do.
order. So these two figures could be like last two before conclusions because they summarize, each point summarizes dynamics which you're going to present next. So it's like a summary of many calculations is being presented before actual calculations.
So effect of the momentum unrestriction is the same in electron and hole, both cases.
Oh, from point of view of
Point of
values,
previous and this one.
they're different, right? There you can see like in
No, I
one
mean,
case
not
it's going from
quality
-1 to
or-
2, in the other it's from -2.
those are different, different
You may
lattices.
keep
Right,
it.
it's you see the difference between different cases. But in quantitative point of view,
Quantitative.
qualitatively they are consistently showing what?
So for holes and electrons, they are relaxing faster for all transitions.
Holes are faster than electrons, independent
When,
whether it's with the same
holes
K
are-
or different Ks.
Holes, no, I'm telling that so when the electron and holes will come back to the HOMO and LOMO, right? They will relaxes, electron will come back to the LOMO and holes will come back to the HOMO. So their relaxation times, they are faster for all transitions, but I did not think about which one is faster, electrons or holes.
First
I
time
need
which
to look
case
at
in restricted or unrestricted? Unrestricted case, maybe, right?
Both, all transitions. When all transition means restricted plus unrestricted.
Hmm.
Okay, so this one is faster.
So what is your dissipation energy?
So how much energy it dissipates when?
So is
How
that
big?
like your excitation energy?
So if electron come from excited to the state to the ground state, it will dissipate energy. Right? This energy is their energy.
To the ground or to the edge of the band?
Edge of the band low.
So it's the difference between
Excited state and
excitation.
Initial
low.
and final.
Okay, so it's like excitation
Energy
minus
difference.
homogeneity.
What homo gap?
Or-
Excited state. Yeah. For whole it is homo. For electron is low. Any question? Any other question? Okay, this is the dynamics figure.
So this is now the intermediate steps which you do to get your to get your
Relaxation
figures,
rate.
which you already
Mhm.
discussed.
Exactly. Yeah, this slide
No movies.
is supposed to be earlier. Okay, now this is the,
You probably need to approach the keyboard and hit enter.
Oh, it's not showing me.
Oh, there is a movie.
so how we have to false mandates.
So in this case, the whole goes slower.
Yeah, I think it's quicker. What does it mean? Like this trajectory is going kind of not just exponentially going to the low state, but doing some kind of
It's a momentum.
So what are the x's?
yeah. What are the x?
What is x and what is y?
X is more.
Ah, it's k probably, right? Or what?
Yeah.
Yeah.
Ah.
X is energy, and Y
Why?
momentum.
Y is energy and X is momentum?
X is momentum, Y is energy. Yeah, I think X is K point, K momentum.
And then
So it's actually the band structure changes with time. Changes.
Occupation of states across the band structure are changing with time.
So is your final state a superposition of momentum states? Is that why there's 4 blurs for the whole state?
Can you read the general?
Oh, okay, yeah.
Initial state.
Or when it relaxes to the HOMO, you see that there's like 4 blurry states. So I'm assuming each one of those is one of the K points.
Yeah.
is
So
your
it's-
band
So
It's
flat?
because it's more flat.
yeah, it looks pretty degenerate. So that's probably why they're all.
Effective mass is
Occupied.
very low.
So you can kind of figure out what is the effective mass of hole and electron and compare. So which one is heavier? Electrons or holes?
Oh,
Yes, you are right.
yeah. Proton is heavier than electron.
It's just slow power.
Okay, and again, you look on the slope. Also it's
Any question?
Oh, you can run it from
Yeah.
advancer.
Okay, now this is photoluminescence. I'm not.
Oh, can you, I apologize, can you go back?
This one?
So what, and maybe one back, one more back, because it has labels. So what is the lowest excitation energy your system is reaching along this dynamics? So it starts, you're excited from like -2 for holes and 3 for electron, about 5 electron
You
volt
mean
excitation.
band H?
so, and you end up in the homoluma, right?
Right? So what's a homoluma here, based on this figure?
It's it looks like minus 1 point something to 1.
What's a 1 point something minus 1 point something, so 2 point something, right?
No, 2 points something something.
Okay.
Yeah.
Yeah, 2 point something. Yeah.
So the lowest excitation is 2 point something. And emission from orange to blue, a transition of electron and hole recombination from orange to blue would be associated with emission of photon of about 2 point something electron volts. Correct? Good. Now let's go forward.
So what is the band number of HOMO in these calculations?
Huh?
I mean, I saw the number in
I think
like
she just
IH
told
is
you.
35.
120.
120.
Oh, you are asking the number of LUMO?
Yeah.
Since the total states 320, LUMO is 160.
So in the, I saw a number is saying that initial LUMO is 110, something like that.
Oh,
Maybe
this
I missed the
initial
number.
states. Initial states.
Initial
electron.
states.
Yeah. I know what you're asking here, right?
Mm-hmm.
So initial states, whole 35 I consider it an electron.
And what is the
And
LUMO?
Jabber, can I, Fatima, can I tell a little addition? So these numbers are not Absolutely.
Absolutely.
It is a number of orbital counting from lower edge of the active window. There could be, it could be like 1,000 orbitals, 1,000 bands, but it's whatever is taken, like 80 or 80.
No, I'm just trying to get an idea about how big these excitation, whole event energy. That's what I'm asking.
But I thought you said that you only have 80 states.
And with 80,
For each
160.
80 bands times 4, 320 states.
Oh, so 35 and 110 also tell you about the momentum.
Yes, so max in
Okay.
this window, in this range, highest possible excitation will be from 1 to 320.
Oh, okay.
And IH35, it's like divide by 4,
10 bands.
9. So from 9th band, keep.
But
So 110 means second K points and 30.
Exactly.
Right.
That's how it should be
Wouldn't-
calculated.
Modular algebra. So everything's mod 4.
Yeah.
wouldn't then 110 be in the
110 divided by
the
4.
occupied? Because 80 times 2 is 160. So that's when your unoccupied states start.
Oh, I guess
Another,
it's 320 of each, or yeah.
I probably was decepting everyone.
I think
Counting.
electronics-
IH and
Oh,
IE
they start
from
oh, okay.
Oh,
Okay.
So one is counted from home,
Okay.
another counted from
yes,
the bottom.
upwards and downwards. Yes.
Okay.
But
Oh,
your initial, your zero is home and luma, or
One,
in
one.
one case it's luma, in the other case it's the
No,
lowest.
no, no, no. Homo luma excitation will be like 1-1,
Mhm.
and high, I was,
you go-
I was wrong.
you go to the
And,
opposite
top
state.
excitation will be
Going down
160 to
the
160. Yes.
So here we can see this is homo, no, this is homo and this is homo. And there are like,
Renumbered once again later, right?
so this is number 1 for whole
Mm-hmm.
and upward it was 35 I consider. And this is 1 for electron and I considered 110.
Okay.
Okay, and I need to divide 110 by 4, then I can get which K point it is.
So maybe I'm a little bit confused, that's why I'm. So initial hole, yeah, isn't it initial hole and initial electron shouldn't be in the same K points?
It's initial
No,
excitation. Do you preserve the K?
Preserve.
Logically, yes. Logically, yes. But there is no ban. There is no. The code doesn't forbid to explore situations when they don't
Oh,
get
okay.
set.
Why same? Because we are considering different.
But if it's photo excited,
And we already agreed that photo excitation doesn't change.
yeah, your
Mhm.
fundamental assumption is photo excitation does not change K. So then you should impose that K does not change.
Is it in video is it in the same K point?
In video, yes, they both started gamma point.
EE. Oh, okay, so this does different thing.
No,
Huh?
this is for.
Let's go to
In
video.
E script is showing the
This
different.
is
K point.
now you go from home to luma, right?
This one?
Yeah, in this 35 and 110, that means they are different K points. But in video, it's showing that it started from the same K points.
Yeah. Video for different states and this dynamic figure is for different states.
Oh, okay.
Okay. Anything else? This is photoluminescence. I think I don't have enough idea, but if you ask me questions, if I don't know, then I'll simply say I don't know. So here, this is the time resolved radiative transitions. You can see here, this one, and this is the time resolved spectra for photoluminescence calculation. And here there are 4 oscillator strands.
So the
For
equation,
40 points.
equation on the top gives an idea how what you are computing, but it doesn't include summation over. It doesn't include momentum, so it probably needs to be updated.
This one.
This also doesn't have momentum.
Okay. Yeah.
So
Here
I-
this is oscillator strand.
Huh?
Do you not include population of the homolumo?
Probably this equation is not quite applicable here. And
No, but this is through time.
let me play a jerk and ask a killer question.
Population times solid strength.
So important.
It's energy times.
When you show greenish figure,
I think
your lowest excitation was 2 point something. So it should emit at lowest optical emission should be at like 2.3 electron volts.
No,
And here you're showing ranges from minus 0.5 to 1.5 on the left, and in the right panel from minus 2 to plus 2. So you're not showing range which would display most important optical transition.
So you mean I need to include band gap?
brightness.
You increase the range.
Because it's probably not just a solid strength, it's a slight strength times population.
Can you explain to someone?
Equation is not applicable, right? It's
It's-
not what is she's really calculating.
So you do.
This is not wrong, but it is for a little different approach.
You do look at population.
I don't have much knowledge
Yeah, you
about
just replace the energy.
population.
Yeah,
So
you
how
want
you
to-
how you include your population? You take HOMA minus LUMA population? Or what? Because you find the slight strength between LUMA and HOMA, right? At the moment, at the specific moment, right?
To the next slide.
Yeah, whatever the occupied states are. So whatever the oscillator
Yes.
strength is
And explain.
between.
No, you take at the moment, whatever, T1, right?
Mhm.
You have your energy 1, energy 2, or whatever, energy HOMA, energy LUMA, right?
Mhm.
And and of course the orbitals, and you calculate the oscillator strength. And then you multiply by the population,
The occupation of a state. That's certain.
but which state because you find the difference between them, like it's two involved. So how you involve the population then?
The transition energy is the energy difference, but the emission that you see is.
Fatima wants to attract everyone's attention to equations here.
So this one is,
No, just equations, not figures. It's exactly what you are
time
discussing.
integrated emission, this one. This ij is number of orbitals, transition between two orbitals, I and j, and this is the total.
So you take the difference between population
Right.
of HOMA and LUMA. Yeah, this was my question.
So this difference in the curly brackets is difference of occupations for valence and conduction band. For given
But
orbitals.
shouldn't be they equal to each other to really be the maximum?
No. This
Like all
term,
holes and all electrons collapse.
this term will be maximal if there is an inversion of population. If electronic orbital is occupied and
No,
orbital is
but-
empty. If it will be 1 and 1 or 0 and 0, there will be no transition.
But holes are empty by default.
Well, state orbital in the valence band must have occupation.
So you should have a hole in a HOMA and you should have an electron in a LUMA,
Right.
then they collapse.
Then
But
there
if
will
your
be-
HOMA is not having a hole, they cannot collapse.
Exact. So it should be inversed population.
But
It's a standard term for lasers.
you call population,
Inversion of population. It is exactly what you are telling. When electron is on LUMA and hole is on HOMA. Inverted
but
population.
your population are not inverse of anything. They're just regular population as you get it. But because
No
population,
inversion in ground state. When there is an electron in HOMO and there is nothing in LUMO. And if they are inverted, if there is an electron on LUMO and nothing on HOMO, population is inverted and system is ready to emit.
Oh, same thing.
Because then that
different
term's equal to 2.
different term.
Where if the HOMO's filled and LUMO's not, it's equal to 0.
Mm-hmm.
And any combination between that will give you a float number between
Right.
0 and 2.
Yes.
So then your rho is like psi squared times psi squared to get like
What's called? Upside square.
Size.
Or is it like is it this way or is it this way?
It's just a transition energy between like LUMO plus Y and HOMO minus X.
Well,
Occupation. He's asking,
Occupation.
Levi is asking about occupation, rho, sub JJ. And
Oh, never mind.
so do you find like the expectation or do you do like the diabatic credit?
What?
Where like you have your cat and draw this way, gives you a number, this gives you a matrix. With like side and side.
Okay,
It's
Then
a
we go
diagonal.
further.
I've got your question. I am ready to answer. So you are speaking on a language of density operator. Density operator can be represented in a basis. If you represent density operator in a basis of orbitals, it will be a summation of terms with ket and bra for pair orbital times expansion coefficient, which is a number. And this number is an element of density matrix.
Okay, so this
But
is,
we we neglect intentionally of diagonal elements of density matrix. We keep only occupations, only diagonal expansion coefficients for the density matrix. Does it answer your question?
yes.
So I'm just wondering, did you consider the momentum of, because I saw that when you calculate the whole is dispersed in a different momentum, but electron is localized on the two specific momentums. So did you conserve the momentum during these calculations?
No,
Because for recombination, isn't it necessary to hold an electron in the same momentum?
Well, the
I'm
oscillator
not sure about that.
strength would just be zero then.
Hmm?
The oscillator strength would just be zero.
It's expected, right? You expect that if you have different case, then your oscillator strength should go zero.
So the equations that is being shown here do show indices ij without momentum. Momentum should be added there. But due to symmetry that is originally introduced into optical transitions, only those that keep
The same momentum.
the same momentum will be non-zero and will enable optical transitions.
I'm just curious, if you really calculate these terms, would they really be very close to zero or not? Just for, because again, your symmetry should be held for the DFT calculations as well, right? So then if you include these non-zero terms, include these cross terms, you should just get very, very small. Of course, you will not get zeros, you will get numerical errors anyway. So you will, but the question is, would you really see something like 10 to the minus, I don't know, 6 minus 10
It's really interesting to check.
or not? So technically you can include into this procedure the transitions with different case
Right.
and check whether these transitions will provide you very, very small oscillator strings. In other words, including them should not change the result at all.
Yes.
Or you will include and see very big difference, which means something wrong with your code.
Or it will be a big discovery. Violation of momentum conservation.
and next, this is for silicon 111. I considered same initial states for this. So
And the Y range should be expanded as well, right?
it was expanded, but I didn't see any feature.
Even if there is nothing, it's better to show for consistency.
How do you get negative emission?
Another discovery.
Absorption?
Negative
Maybe
emission is
I-
either absorption or
Antiphoton?
opportunity to improve the flow.
So this is dynamics of excited electron hole pair, right? This one. And this is the integrated emission spectrum.
Wait. Let's focus on blue figure first. And
Okay.
so it's occupations of electron and hole multiplied by energy difference, right? So it just shows as excitation relaxes, including all involved electron hole pairs. Okay.
And then this is the integrated emission. If we consider this one with the one for silicon 001, we can see that this is more intense. And see, it is not comparable.
It's very strange what is on the right panel. What are X and Y and how they are obtained?
This is wavelength, and this value is times 10 to the power 5. And this
So
is
something has to be improved in this figure.
I'm sure it's wavelengths, maybe it's electron volt.
nanometer.
But I see what it's saying, but if you look on the numbers, 0.5 nanometer doesn't make a lot of sense.
This is times 10 to the power 5.
Oh, 10,
Yeah.
Oh,
10 to the plus 5, right? So it's
Plus
actually,
5, yeah,
then what is it?
infrared.
Super.
So it's
Super infrared, but your gap is open or closed in this case? For this system. I think you looking on the systems which have open gap around 1 electron, more than 1 electron volt, right?
No, but it looks like it's half to a quarter of an EV. From her blue plot.
Yeah, blue, but we're looking on the right floor.
Yeah, but what is
The value, well,
quarter of an EV?
500, what it is, 5 to the 10 4, 50,000? Yeah, this is 50,000?
No,
So this
it's
is
4,000. Because it's 0.5, so you do 10 to the 4th. So that'd be,
so 2.5.
50,000.
it should be 4,000. 4,960.
40,000. It's 40,000, because it's 10 to the 5th.
Yeah.
1.5, 10 to the 5th, it's the same as 5 times 10 to the
So I'm
4th.
assuming that maybe it's supposed to be 10 to the 5th.
So how this figure was obtained? Mechanically.
So it's a deep infrared.
Which part of the
No one is, right?
I have probably this is wrong. I don't know. I need to check.
right now it looks like so
So it's
your
probably not-
bluish stuff is matrix,
Like a quarter of an EV.
It's kind
and
of point
you
one,
integrate along one dimension and keep dependence on another one just by summation, right? But maybe you flipped and integrated over the opposite direction.
from the
I think so. Yeah, I checked.
So this one
It
needs
was
to-
like x-axis
This one
plus
needs to be
intensity.
rechecked very carefully. It looks like two indices were flipped.
Yeah.
So you have disagreement between blue and blue. I mean, right and left panels do not agree, right?
This axis should be flipped.
Not axis on the image. Axis
Yeah.
during the procedure when you compute integration.
Or you're saying that intensity should be on the bottom and
No,
right
no,
ones on the top?
Intensity
That
should
makes
be.
sense.
Intensities will be x and frequency will be y, and time should be integrated out. Maybe right now that
She was
x-axis-
integrating something different,
Yes.
not time.
Well, I do not know, but there is a suspicion.
Is it the last slide? No?
Almost.
Oh!
Yeah. So conclusion is about that relaxation rate. Electron hole relaxes faster for all transitions. And that's all.
So
Okay, but thank you. Does anyone has steam for more questions?
So in conclusion, when you said they have a additional pathway in indirect transition, what's that additional?
So for
That's the indirect one, then what's the action of it?
Pathway.
indirect, right? So if it is direct, then just same K point channel. If it is indirect, then
So it's just
same.
indirect direct.
Times 4 in your case, right?
Many thanks to everyone for supporting discussion. If you are taking critical notes, you can submit them to authors. And we are meeting next time Tuesday 4 p.m. with first rough draft of SiNW
What is the
poster.
system, I mean, in the XYZ? Can you? The coordinates. So you take into account that the idea is that you can take much larger piece of code.